UCSD 111, Lecture 1, Set 4, we'll be talking about hardware description language, its evolution and usage. Hardware description language was born because before using this hardware description language, designers used to draw circuits or write gates, transistors, and generate layout by hand. This was, of course, a very tedious task. People realized that just like software, for example, C was a recent programming language at that time, they realized that if they have a C-like programming language, that would make things much easier for them. The task of the digital designer after creating this type of language then would be to determine which part of the code will be a sequential, which uses parts of the memory, and which parts will be combinational, which will be going into details in the next set. But then the nice thing is this tools would actually take this description, make a high-level circuit, and go through the compilation of this into a piece of hardware, which is called the synthesis process. And not just that, the HDLs, they also enable us to test and verify these circuits that we've written in these programming languages. In short, we can use an HDL language for both simulation and synthesis. And the two most widely used hardware design languages are Verilog or System Verilog, which is an enhancement of the Verilog we'll be learning in this class, and VHDL. Let's see how these two languages have been developed throughout the years. The VHDL, it started as a US DoD project. They felt the need in early 80s that they needed this scalability for the digital design, so they asked for the performers to design such a language. The main performers for development of this were IBM, Intermetrics, and Texas Instruments, who worked on designing this language in 1983 to 1985 timeframe. Around 1986, all the rights for this language was transferred to IEEE, and the standard was released in 1987. And it has been updated, the standard has been updated throughout the years, as you see on this slide. Verilog has been kind of going in parallel a little later than this, but Verilog was independently designed by the CAD or computer-aided design companies, which was basically Gateway Design Automation. It was acquired by Cadence a few years later, and then there was the born of Accelera, which is maintaining and sustaining the Verilog language over the years. It became an IEEE standard in 1995, so after a few years after the VHDL, and it has been going through the revisions, and the system Verilog was finally introduced in 2013. So the Verilog and System Verilog has merged, but the latest standard for System Verilog has been released in 2013, which is the language we'll be using in this class. So if you, there's a choice of which language to learn, obviously, and we chose System Verilog because System Verilog is much more used in Verilog is much more used in the United States. VHDL is more used in Europe, and most of you guys will hopefully take a job in US. I have to note that the two languages are similar enough that if you know one, learning the other one is way easier than starting from scratch. Just like if you know a C language like C and you want to learn Java, it would be much simpler compared to someone who's starting from scratch. The verification and synthesis is relatively easier and more concise using System Verilog, and these are the feedback that I've got from people who are using both in industry. The HDL is actually there are extensions for creating analog mixed signal models in Verilog, which is also useful if you're designing mixed signal circuits. And we can use this language both for design and verification, which is another plus for this language. So in summary, we can design the transaction and registers, and sometimes we just do that for simulation, and not everything we do for simulation is transferable to a synthesizable piece of hardware, as we will see in the next set. But it can help us to get also synthesizable register transfer level and gate for the designs. And then not just that, we can get test benches and verification, and some of those steps are again not synthesizable, but useful if you're designing in particular a big system, because as we mentioned earlier, unless you're able to test and verify things right on the go, it will be completely undoable to test and verify a big system that has not verified the smaller components as we design things. We will be talking about the digital design basic and gets our hand into basic Verilog programs in the next set.